Everybody to this first afternoon session. So the first talk is given by Alfred Hero from Michigan, who will tell us what the tensor graphical lasso is.
Yes, thank you. Right, so I'm going to talk about the tensor graphical lasso. It's in the context of dealing with heterogeneous data. That's one of the forms in which heterogeneous data comes to us, which is heterogeneous indices, so space and time, space wavelength, gene probe index position on the chromosome and time and so forth. So in those types of problems, there's an intrinsic structure that exists in the data array that tensor graphical lasso is designed to exploit. So that's what I'm going to talk about today, and I'm going to bring you through to the tensor lasso in as gentle a way as I can. I'm going to start out with just looking at the multi-index data array as a set of multiple indexed scalars. And we have k different dimensions, d being the overall product of all the dimensions. So if you wanted to arrange this array into a big matrix, it would be a D by D matrix, where D is the product of all the internal dimensions, the k internal dimensions. So these are very large matrices, and one cannot hope to train models on such large matrices that have as many degrees of freedom as the matrices themselves. And so the structure that we're going to be looking for is models, namely that reside in the covariance or inverse covariance of these data arrays that can be used for these types of applications. So predicting gene expression over time for a very large number of genes that are indexed over gene index in time, weather from spatiotemporal climatological data. I'm going to show some examples from that in this talk. Gate detection from low-resolution video, crowd anomaly detection. All of these applications have the common traits that they have multiple indices that are indexing over different types of domains. It's not just that the indices are multidimensional. It's that the domains are very different. Time behaves very differently from space, and when you look at the types of structure, the types of correlations, the types of dependencies, local dependencies, linear ordered in time, not linearly ordered in space, and so forth. The content of these arrays is very complex. There might be multiple populations, clusters, classes, and very high dimensional. And then the content may be noisy, very high variability, because we do not have either a sufficient number of replicates to replicate this array enough times to be able to form a model with low variance parameter estimates, or it may be that that there might be missing values or other types of noise. Okay, so my main point here is that first order models are not sufficient for this problem of highly complex data, and that much information lies in the covariance. So that's, if you believe that, then you'll believe the rest of my talk. So this is what we're faced with when you look at this multi-indexed arrays for just two dimensions, say indexed in space and in time, where I've lexicographically ordered space into a linearly ordered one-dimensional set. So if you unpack this S by T matrix, which I call a matrix for some epoch, where epoch may be the epochs might be, for example, corresponding to different days on which you take these samples of a temporal window of space, and you then unwrap this into a vector, which is going to be a vector of dimension S by T. You look at the covariance, that is the joint variation of the elements of this vector in terms of their second order variations, and you get this covariance matrix, which is S by T by S by T. I've denoted here, because this is going to become very key in building models, that because of this multi-indexed attribute, that in this two-dimensional case that I'm showing here, we have patterning, right, in this covariance matrix. And that patterning, because of the way it's been organized in going from successive columns concatenated on top of each other, each one of these sub-blocks corresponds to a correlation in space for a particular pair of times, right? And so we have this characteristic blocking of the matrix, which is going to suggest block-type models, and the block-type models that we're going to explore are Kronecker types of models. So that's the covariance, but if we want to estimate any parameters or learn the behavior or patterns in that covariance, we have to do that with data. So let's say we have n samples from this spatiotemporal array that I've denoted Z11 through ZD1. D is the dimension, S times T, right? And so we can then form the measurement matrix, which I call Z, with columns equal to each one of the samples going over the variables, those variables being space in this case, or maybe space and time, or maybe gene index or other type of index. And then we can form a sample covariance matrix, which is also D by D, that has this form here. And you have to, in order to even form the covariance matrix, you have to have n equal n greater than 1. If you form it in this fashion, by normalizing by n minus 1. If you normalize by n, you can get away with n equals 1, and I'm going to show that we indeed, in the Teralasso method, that we can estimate properties of the covariance because of this repeated block structure with only one sample. So that's the covariance, sample covariance matrix. So the empirical estimation of covariance requires some methodology for finding an approximation to the true covariance from the sample, and the sample covariance is the best statistical compression of the data under the multivariate normal model, which I'm going to assume for the remainder of this talk, although the results in the papers that I cite are not all restricted to the multivariate normal case. But the multivariate normal model has a log likelihood function of sigma, this covariance, that depends on the inverse covariance through the log determinant and through the trace of the product between the inverse covariance and the sample covariance. So maximum likelihood estimation is basically a solution to a convex program, right? If you don't have any constraints, no structural patterning that you will impose on the matrix or penalties that will softly impose those patterns, then this is a very large convex problem with large in the sense that they're on the order of d squared unknown parameters, which can be enormous, which can be in the millions of parameters for reasonable spatial and temporal extent of our measurements. And so the requirements even to sort of get going with this maximum likelihood estimate, which is unconstrained, is that we have to have at least the number of samples n exceeding the number of dimensions, or else you don't even have a well-posed optimization. There's no unique solution. For the estimator to be accurate, there are well-known high-dimensional results on statistical accuracy of maximum likelihood estimates, and this is one of them for the mean Frobenius norm of the error, the estimation error from the maximum likelihood estimate that comes from inverting lambda omega hat is going to decay as basically d squared over n. And so you can look at this as sort of defining a kind of a phase transition where if n is significantly less than d squared, you're going to have uncontrollable mean squared error. If n is sufficiently greater than d squared, then the error will decay to 0. So this is a threshold phenomenon that we're going to see in a few minutes. So, of course, we can impose additional structure, and that's the whole point here. And the structure we're going to impose later on is this block structure I explained. But with, for example, this type of structure of toplets or low rank plus identity, so Tikhonov regularization approaches to the problem, or sparsity without any particular type of patterning where the number of non-zero entries in the inverse covariance or the covariance is of order D, low rank plus sparse, and so forth. That gives you a threshold phenomenon which is much more desirable, where you only need on the order of D measurements as opposed to D squared, right, in order to be able to control the accuracy. So there's lots of prior work in this area, and I'm not going to talk about the prior work in any detail other than to say there's a lot of work on looking at structured covariance estimation with banded models or sparse eigendecomposition models, Stein shrinkage models. Some of that work appeared more than 12 years ago. And sparse inverse covariance models, where you model the inverse covariance instead of the covariance itself, which are also called Gaussian graphical models under this framework where we're assuming that the samples come from a Gaussian multivariate distribution. You can have sparse models such as a Kronecker Gaussian graphical model, matrix normal model, sparsity testing, where you're not looking to estimate the covariance, but rather to detect where the sparsity occurs in that covariance. Inverse covariance sparsity testing, where you're testing for the same thing but in the inverse. So one can relate this to graphical models simply by identifying the equivalence of a covariance matrix with zeros or an inverse covariance with zeros, depending upon whether it's a covariance or an inverse covariance graphical model. And you can then write down a compact representation for these covariance or inverse covariance matrices in terms of a graph, a chain graph, for example, that corresponds to a tridiagonal matrix, or a interleaved block diagonal matrix that corresponds to a graph that has two cliques separated by some separator, in this case variable 3, and so forth. So you can identify then the model directly with the structural constraint that describes that is given by the topology of the graph, and that can tell you where the zeros are in your covariance or inverse covariance. And whether you deal with sparsity in the covariance or the inverse covariance is a matter of taste, perhaps, but I would argue that, and I will argue, that sparsity is more reasonably assumed in the inverse covariance than in the covariance. And that's because in the sparse inverse correlation or covariance method or model, you're looking at conditional dependencies as opposed to unconditioned marginal dependencies. And the conditional dependencies that describe things like Markov random fields, for which autoregressive processes are one of a category. Global latent variables, which are not Markov random fields, but can be conditioned to have a structure like that. And just to see if I can convince you of this, I take a particular example of a physical process. So I make the bold claim that most physical processes are sparse in the inverse covariance. And by example, I pose the hypothesis that we are looking at a space-time process that obeys a Poisson equation, right? So Poisson equation describes, the Brownian motion in semiconductors, or heat transfer, or hydrodynamic fluids, and this differential equation, the partial differential equation, can be decomposed using the Euler method into finite difference equation. And then if you represent the finite difference equation in the form of a noise process, W, Brownian motion process, that is driving X, which are these lexicographical spatial measurements, I and J are spatial coordinates, driving X through this sparse matrix I minus A being sparse because this partial differential equation is defined locally, right? It's the neighbors of grid points that, that influence their neighbors. You don't get global dependencies, and so thus you don't see for pixel ij at time t any other pixels that are outside of the immediate neighborhood of that particular pixel ij involved on the right-hand side. So this matrix A is going to be sparse, and now if you write the covariance of X from this equation, you immediately get it that it's the inverse covariance that has the form of a outer product of a sparse matrix. The covariance is not generally sparse. The covariance is going to be the inverse of this sparse matrix. So in this particular case, it's a pentadiagonal matrix because of the local neighborhood structure. And so this is just a graph representation that indicates this local dependency structure that defines the Poisson dynamics, the dimension of the Poisson equation, and then the corresponding adjacency matrix that has this pentadiagonal structure. Okay, so that may or may not be convincing to you that this is a universal property, but it has certainly been observed in many applications that the inverse covariance tends to be more sparse than the covariance. And this is just a case where this is a realization from this Poisson random field. All right, so that said, we're going to be modeling the inverse covariance. And so let's go back to this picture. The model that comes to mind, since we have this block-structured patterning, is a model that basically sends regularity into these patterns over, say, the spatial domain, and then maybe weights the spatial domain small covariance matrices with some scalars that then represents a low-dimensional model for this high-dimensional spatial temporal covariance. And indeed, that's the Kronecker product representation, right? Where you effectively inject a matrix, a small covariance matrix B that is, say, Q by Q dimensions, into a matrix that is PQ by PQ by applying another matrix A in a Kronecker product left operation to B, and then you get this type of replication. So this is a very sensible model to start with. How realistic it is, that's something that remains to be shown, but it's certainly probably one of the simplest ways that you can induce a lower dimension into the model. So notice that the number of unknown parameters here, instead of being PQ squared, is P squared plus Q squared, which can be advantageous when P and Q are of highly different magnitudes. So the Kronecker product properties, there's lots of nice ones. A Kronecker B is positive definite if A and B are, which means that we have an invertible Kronecker product if the factors are invertible. And in fact, the inverse obeys this really nice relation that the inverse of the Kronecker product is the product of the inverses. The determinant of the Kronecker product is equal to, I don't know why that's the not equal to, that should be an equal to, the determinant of A and the determinant of B. That slipped in from another slide that I'm going to present later on. And then this is another property which we're not going to use here that allows you to do things like singular value decompositions on these multi-indexed arrays, and I'm not going to talk about that for lack of time. But this is just sort of a notional example. If you have the Kronecker product of a 3 by 3 times a 6 by 6 covariance matrix or inverse covariance matrix, the case may be, since we know we have this inverse relation, that we have an 18 by 18 covariance matrix, right, 3 times 6, which has 153 unknown cross correlations. That's that means we're going to need at least 153 samples or 153 squared samples, depending upon whether we're striving for just sheer invertibility of the sample covariance, or if we want accurate estimates of this covariance matrix in its product form. So this leads to an unconstrained a Kronecker maximum likelihood, which has properties that are much lower dimension, right? Fewer dimensions required. 3 plus 15 being 18. I forgot to say that, right? So 153 unknowns in the unconstrained covariance matrix. Only 3 plus 15 unknowns for the block Kronecker matrix. So we've gone from 153 unknown parameters to 18, which is a significant order of magnitude improvement in terms of the number of required samples that one would need in order to estimate this model accurately, assuming, of course, that this model is sufficient to describe the underlying data model. If you impose sparsity, you can even get this down further, where we go from, in this particular case, I have a sparse, again, 3 by 3 and 6 by 6 matrix. We go down from 153 parameters to 7 unknown correlation parameters in this case. This then leads to what's called the Kronecker graphical lasso. The graphical lasso is the unconstrained version of the Kronecker G lasso. So this is like a L1 relaxed estimate of the inverse covariance matrix where the relaxation is on the sparsity penalty. In other words, the L0 penalty. And so if you look at this, you have x and y are the Kronecker factors of the inverse covariance omega. And then we have this constraint that we have omega, the 0, L0 is equal, it should be equal to, not less than equal to, order PQ. This big O, of course, already contains a less than or equal to in its very definition. And then the maximum likelihood consists of minimizing the negative likelihood function, which takes this form. I just plugged in the x Kronecker y in the place of omega or sigma inverse in the previous equation for the likelihood function unconstrained, right? Under no particular constraint on the form of the inverse covariance. And we have these two tuning parameters, lambda x and lambda y, that control the amount of sparsity that we want to impose on the left and right Kronecker factor that goes into describing this inverse covariance. This is something that this is called, this can be called various things: transposed regularized covariance, the KG lasso algorithm. It's also been called the flip-flop model. That's an artifact of the fact that the authors of this, it calls it a flip-flop model, used a alternating minimization algorithm, flip-flop algorithm, to find the x and y parameters, so an approximation to this minimization problem. So of course this is not a convex problem, right, in x and y. We have bilinear in x and y here, so it's not convex, but there have been a number of approaches to try and at least define an algorithm that's guaranteed to converge to a local minimum. This is one of them, that by a student of mine now at MIT Lincoln Laboratory, that has complexity of p cubed plus q cubed instead of p cubed q cubed in terms of runtime. And you can show convergence, algorithmic pointwise convergence, that it converges under conditions that this sample covariance is positive definite, it converges to a fixed point. And then we have statistical convergence, assuming that the algorithmic convergence holds, which then gives us this order p plus q over n type of rate. So that's this not even order d, but order log d in a sense. Well, not really log d, but not d instead of p times q is replaced by p plus q. And then you get this just shows these phase transitions I was talking about, where n has to be equal to at least p to the fourth if you have if p is equal to q, right? So the Kronecker components are equal to p and a q-dimensional matrix respectively, so that the unconstrained matrix has p squared entries. And then, so this just shows how there's an advantage to pushing up on the reduction of degrees of freedom in the model, and the KG lasso being the sparsest version of a Kronecker model, Kronecker product model, gives you the best, minimizes the unachievable region, right, in n and the number of dimensions on one of the Kronecker factors. And then this just shows an application to a wind speed prediction problem where you have a 10 by 10 patch from the Arctic to origin sea, and then you form then a spatial domain of 100 pixels, 100 pixel locations, a time window over 2 days. There are 4 samples per day from this National Center for Environmental Prediction Data. It's part of NOAA under the Department of Energy, and then 224 possible time samples over a period of 5 years or 4 years. And this just shows the zonal and meridional components. Actually, this is just the zonal component u. There's another component of wind speed as a function of latitude, longitude, and the time that the sample was taken. This just shows you the raw data. One then can represent the raw spatial covariance matrix, or standard covariance matrix, I should say. Not spatial. This is spatial and temporal. Both. You can see now this sort of Kronecker, or this pattern form I was talking about before, with these small, very similar types of patterns in each one of these blocks, these 100 by 100 blocks. So those are spatial blocks, and so each block corresponds to a correlation under the Kronecker model, under the temporal correlation coefficient times that block. And so you can see then that if you apply this Kronecker product approximation to this, in terms, this is the maximum likelihood estimate, that you very closely approximate the standard covariance matrix. And here is the left and right factors, temporal factor, which shows that we have a temporal dependency that decays rather quickly, and a right factor, which is the spatial correlation factor. Each one of these small 100 by 100 blocks in the matrix above, that shows that as you go towards the North Pole, that everything gets really correlated together. So the North Pole is over here, Sweden and Norway are up there. So that's just sort of an indication, and this just shows that if you use this Kronecker method, Kronecker PCA here is this is a just using a factored model, which I won't discuss. It's the same as the maximum likelihood. We only use the most significant Kronecker PCA component, that you get better tracking over time of the weather patterns from this 10 by 10 domain, spatial domain. So we also applied this to crowd video. So here we have a staged event where you have a crowd that's on the left is just milling about, and then at some appointed time they all start running away. And the objective is to be able to automatically detect that there's an anomaly, and then these others are similar types of anomalies from the CMU crowd video data set. And if you look at the likelihood, the predicted likelihood using the maximum likelihood estimates of the Kronecker product, you can see a very significant anomaly bump in the negative likelihood at approximately the time that all the crowd starts to disperse. This just shows another example where we have a cell cycle data over 9,000 genes, so there's 9,000 variables at 36 time points. That's about almost 36,000 dimensions, and with only three cell cycles, you can find this. This is I just show this to indicate that for the temporal component of the factor model, you pick out the circadian rhythm right off the bat. So these models are really tuned to zoom into particular characteristics of each one of the dimensions. And what is the characteristic of the time dimension that dominates in any living cell? It's the cell cycle, right? So this shows that it picks that out. So tensor graphical lasso is a model which gets around one of the major issues that I mentioned just a minute ago, and that is the non-convexity of the objective function. So why does this work? Well, Kronecker products have this bilinear dependency. Kronecker sums, which the Teralasso model uses, are linear. So the Kronecker sum representation of a covariance matrix is Kronecker sum B is basically A, which is then projected into a higher dimensional matrix through an identity matrix on the right-hand side of the Kronecker product, and plus the right factor being projected by the left-hand side of this second Kronecker product into an m-dimensional space. And here, all the dimensions are compatible because this is an m by n matrix, and so A is m by m, B is n by n. So this type of model has been explored. What we contribute is that we extend this to an arbitrary number of factors, which is going to become important when you look at spatiotemporal models where you want to model longitude and latitude independently, so those correspond to individual dimensions, instead of simply lexicographically ordering the longitude and latitudinal indexed spatial array. And also we come up with a much better, much faster convergent algorithm based on iterative thresholding. Properties of the Kronecker sum, it's associative, so it doesn't matter. This allows you to generalize to more than two Kronecker sum factors by simply computing the k-1 Kronecker sum and then taking the Kronecker sum of that k-1 in some new k factor. Here k equals 3. It's linear, as I mentioned before. It has a distributive property, which is a little strange. It's not the standard distributive property. And it has a nice eigendecomposition property. It has some non-properties, however. So just show this as an example so you'll see where these non-properties come up. 2 by 2 factors A and B. The Kronecker sum and Kronecker product are 4 by 4 matrices on the left and the right. So one thing we can see right away is if that A is equal to B, A Kronecker sum B is no longer positive definite, right? So in particular, we lose the nice inverse property, and here's that not equal sign that crept back a few slides ago, that shows that we don't have these nice properties of the Kronecker product. The determinant of the Kronecker sum is not a simple function of the determinant of each one of the factors in the sum. So why do we want to use this model? Well, one of the main objectives in finding flexible models is being able to control the complexity. And the complexity here is really the number of edges in this graphical number of non-zeros in the covariance matrix. Hi, Ben. The Kronecker sum, this is for 3 dimensions. First dimension has a covariance or inverse covariance structure that obeys this type of graph that I have up here. So variables 2 and 3 don't have an entry in the inverse covariance in the 2 and 3 component in the first factor. And so we have these 3 factors. And so if you look at the ordinary Kronecker product that's been investigated before, you get this kind of interleaving and massive explosion of dependency because of this. That you take the factor B and C, and you're basically embedding the entire matrix replicated a number of times equal to the dimension of dimension squared of A into the matrix. Whereas this Kronecker sum has a much sparser representation. It doesn't tend to produce as many edges. And so what we'll see is that this allows us to have better sample complexity, that is, fewer samples required to estimate the Kronecker sum. Of course, again, the Kronecker sum has to correspond to, at least to some extent, to a real model, and I'll hopefully convince you of that when I wrap up in a couple minutes. So we have an estimation scheme, as I told you. Teralasso minimizes the negative log likelihood. This is just showing the we're not penalizing off-diagonal component, the on-diagonal components of the covariance, since those are variances. We're not shrinking the covariance. We're only shrinking the off-diagonals, the cross covariances. MK here is the product of all the dimensions except for the kth dimension. That's what MK is defined as. Rho k is a regularization parameter, much like lambda x and lambda y were in that I was presenting a minute ago. This is just the sample covariance. Notice we were normalizing by n and not n minus 1. And then we're minimizing over the positive cone, right? So that's the point. And so we have this first order method, the FISTA method, that in addition to another method I'm not going to talk about in the paper here that's on the archive and has been submitted to a journal. So we can prove convergence rates. I'm not going to spend time on this, but this looks somewhat similar to what you get with the Kronecker G lasso or the graphical lasso, except that instead of log p, you're going to have log p squared if you have 2, or log p to the k, I should say, if you have a kth order Kronecker sum factor, Kronecker product factor. So that would be k times log p. And then what we have in the denominator is the minimum of this dimension product that I mentioned before. So this corresponds to a significant decrease on the theoretical convergence rates of the accuracy of the estimator. So these are strong concentration type bounds, so that this holds with the probability that's specified. So we're faster by this factor of min k mk, which can be very large. It's the product of all the dimensions except for the kth dimension for the minimum factor dimension, as opposed to being simply the dimension. Okay, so this shows comparisons for a random Erdős-Rényi type of matrix, a graph that's corresponds to an Erdős-Rényi, has a certain number of edges. We then take those edges, embed them into a covariance matrix, project that covariance matrix onto the positive cone with some epsilon, so it's non-singular. And then for various values of k, number of Kronecker products, for estimating this Erdős-Rényi type of covariance or inverse covariance, we see that the Teralasso runtime scales quite nicely. We can handle up to 1 billion variables. P is equal to 1 billion with with 10 samples and all the decays equal to 65 with 5 Kronecker products in only about 124 seconds, right? So very fast algorithm that can handle immense numbers of variables, speed ups on order of 4 orders of magnitude, and we get this type of comparison. Ben's starting to annoy me here. Sorry. So as it compared to the scaling, the number of computations is the product of the cube of all the dimensions. It's basically the sum of those dimensions. And that's where we're getting this significant speed up in terms of the runtime. So I just want to terminate again with this spatial temporal data from the National Center for Environmental Prediction, this wind speed data. So we look at a 10 by 20 grid, so 200 variables for the western U.S. Note that the Rockies are right in the middle here, or close to the middle. And then for the eastern U.S. And so what we're going to do is we're going to build a couple of Teralasso models. The first one is space alone. We're not going to consider time. So here, the NCEP data set consists of over 50 years worth of data, and we're going to look at from 1948 to 2006, I believe. At the spatial component, sampled at each time. We're going to assume that the time samples are identically distributed and independent, so we can use them to construct a sample covariance with 50 samples. This is over a 1 month period, and so there's 4 samples per day, if you recall. And so this shows for the eastern grid over the eastern U.S. and the western U.S. the latitude and longitude factors, and with their corresponding graphical models that come out of this. And what we can see is, interestingly, that in terms of the longitude factor, we have a break in the model. A lack of dependency or conditional dependency that occurs right around where the Rockies start to intervene in the spatial longitudinal component. And so this could be basically attributed to the fact that the weather in the Rockies is very different from the weather to the east or the west of the Rockies, and so we get this break. We don't see that in the eastern data. This just shows comparisons for different types of estimates, a standard shrinkage estimate in a maximal likelihood framework, but now with an L2 penalty, L2 squared penalty, that introduces shrinkage into the inverse covariance. Here's the Teralasso estimate, the Kronecker sum estimate which is the other algorithm I was talking about, and then this is the Kronecker product algorithm. What I want to draw your attention to is that we pick up a structure that we see much later when we choose when we have 50 samples, even if we only have a single sample. And that's because we have this incredible replication of spatial covariance, right, from this Kronecker sum model across the covariance matrix model. And so effectively, even with one sample, you can perform accurate inference under these types of models. And this is just for the western U.S. We have the same type of phenomenon. This is the last result I'm going to show, which is just a comparison showing that if you use just a spatial-only Teralasso with 2 factors versus a spatial plus temporal Teralasso, and you train a classifier on the month of January, and you train another classifier, you train a classifier in the month of January versus the month of June, and then you look at the ability for an out-of-sample instance of the classifier to classify whether it's summer or winter. Easy problem for most of us, but this is just based on this wind data that you can see if you don't use temporal information, and that's up here in the eastern and western grid, that first of all here we have this very accurate estimate a very accurate classification error, I should say, rate, even for one sample, as I showed you before. With the Kronecker product model, we have considerable degradation below about 15 samples, 15 samples in this case. There's a single instance, and we're just looking at aggregating 15 of those temporal instances together in the sample covariance, whereas here we're only using one instance. If you include time, and here we're including 5 time instances, so this is a bit longer than a day, then the Kronecker product model gets a little better with 3 factors, but we're still very low classification, misclassification error rate with very, very few samples on both the eastern and the western grid when we include the temporal components. It just shows how important including temporal dependence is in order to be able to decide whether the weather patterns are more winter-like or summer-like. That's all this is showing. All right, so let me just conclude with a few comments. The sparse Kronecker product model reduces the complexity to basically a linear p plus q as opposed to the nonlinear p squared plus q squared if you incorporate sparsity. So this is the kg lasso. But the Teralasso is a reduction that where the big O is the constant in the big O is significantly less than the Kronecker product because we have so many fewer edges, right, that propagate because of the Kronecker product multiplication or injection nature of the Kronecker product. Some open questions. We have no idea if the Kronecker sum representation is a complete representation in any sense. So for Kronecker products, it turns out that if any matrix can be represented as a sufficient number of sufficiently large number of Kronecker products summed with the appropriate weighting factor. So the Kronecker products are complete, if you like, in the space of matrices of any dimension. We don't know if that's the case for Kronecker sums. It's an open question. Of course, one can ask about incorporating other structural constraints in addition to the Kronecker sum representation. And then there's linkages that would be interesting to explore to tensor factorization approaches that have been primarily developed for first-order descriptions of the data as opposed to these second-order covariance descriptions. So trying to model the mean of the array with a tensor factor representation as opposed to the covariant structure. So that's the story. Thank you for listening.
Yes, Mila.
Yes.
The replication factor, I mean the ratio between n and p is very, very important in order to obtain some meaningful field.
Exactly, yes.
But is it possible to know it in advance? Is there some estimate?
Yeah, so in this theorem, I don't think I can get back there. This gives you an ability at the very least, you never know these constants out in front, because this is the ground truth, but you know the rates are proportional to these known quantities, right? You know P, that's just the dimension of the problem. You know the MK, you know the sparsity. Well, you may not know the sparsity factor, but you might assume that. And N is the number of samples, right? So this at least gives you the ability to try to fine tune to the rate, not necessarily to the constant in front.
Thank you.
Other question?
Yeah.
So I wonder, can you generalize this to more sort of general sums of Kronecker products rather than the Kronecker sum I cron A plus A cron B plus C cron D and so forth and so on?
Yeah. So that's this completeness result I was mentioning a minute ago. So Any matrix, in fact, has that representation for A, B, C, D, E, F, and so forth as a sum of pairwise Kronecker products. What we don't know is whether the Kronecker sum has that same property. If it did, then we could define kind of a Kronecker sum PCA or, that would have many of the enjoyable properties that Kronecker product PCA has.
And so I guess a follow-up question to that is dimensionality, right? So I can, if I have a big matrix, and I can say I might have different choices of doing the Kronecker product decompositions, right? So size n by n, size p by q, and so forth, right?
Exactly. Yeah, and that's where this this type of representation becomes very important, because if you can sort of simultaneously pose many different dimensionality factor combinations, then they're really only they only scale logarithmically in the dimension, because of the factorization property of the integers. But one could, in principle, explore that using a series approximation with all these different possibilities of modeling. Yeah, it's a good point.
Do you see a chance to do statistical inference based on the tensor graphical lasso, or for instance, looking at temporal dynamics and the spatial temporal dynamics?
Yeah, so that's what I tried to show in this example. Well, certainly in the Kronecker product example, right? This was. So this is, if you like, you could try to fit a temporal model, like an autoregressive model or a ordinary differential equation model, to this covariance, because this is the temporal factor of the overall covariance. And then you'd fit a spatial model to this component. So you can do the same thing with the Kronecker sum representation, except you're going to get somewhat different models, right? We haven't pursued to the extent of exploring this as sort of an initial phase of developing models for temporal and spatial components separately, but that's certainly, this would be a first step that you would take in building such a dynamical model, right, that would fit this covariance. But the result that I showed here, this shows, I think, really cleanly that in this case where we have no idea that there's a circadian component in the data, this high, very high dimensional data, it comes out directly in the temporal covariance. Yeah. Good. So thank you, and thanks to the organizers. I guess I'm an organizer.